statistics and the curve fitting toolboxes. My name is Mike Augustini, and today I'd like to tell you a little bit about MATLAB. In particular, we're going to be focusing on how you can use toolboxes to aid in your data analysis. Now, when I think about data analysis, there's a couple things that come to mind, and it helps if we pull these out and consider them, because it helps put into context the tools that we choose and really the goals of what we're looking for when we're doing data analysis. So to start with, when you're doing data analysis, generally you're going to have some data. In its rawest form, data is just numbers. So the analysis of this data, these raw numbers, is the conversion of this data into something meaningful, something reduced, something with more intelligence put into it than the raw data itself. So to do that, we're going to be exercising different analysis routines. Analysis routines can be done in any package. For example, here you see some MATLAB code, an Excel equation, and some C code. But regardless of what your analysis is, or what algorithms you choose to implement, or what language you choose to implement them in, the process of data analysis is the conversion of data from something raw into something refined. So as we're going along, we're going to be looking at the data, and we're going to be looking at some analysis. So keep in mind these two concepts. In some tools, you will find that when you open them up, you're staring directly at your data, and you have to remember your analysis. You have to remember the algorithms that are hidden behind your data. And in other programs, such as MATLAB, we're going to find the reverse is true. So we're going to be staring at our analysis, staring at our algorithms. We're going to have our process exposed, but our data is going to be encapsulated into variables. All right, so with that, I want to get into some demos, and I'm going to set up all my demos in a three-tier format. The first thing we're going to do is we're going to access our data. This is the first step in doing any process of data analysis, is you have to get your data from somewhere. The simplest place to get it is from files, but you can also get data directly from other devices, such as a hardware instrument, or you can get your data from other software. For example, a simulation that's running, or maybe a database that's running. Once we have this data, the next step is to exercise our engineering and scientific skills. The stuff that we went to college for to train on. So maybe some data analysis modeling, maybe some algorithm development, maybe some application development. So today we're going to be focusing, of course, on the data analysis and modeling. Once we have kind of brought reason to our data, we then need to find a way to share that information with other people. So the simplest way, of course, is via report. Put your information together, but also other ways to share can include deploying applications, or perhaps just sharing a number or two that you've got from your analysis. Along the way, we're going to be seeing how we can use MATLAB to help us automate these tasks, where we can be creative and explore our data analysis, and ultimately, with the click of one button, go from raw data in the file to some sort of shared output, for example, a report. So with that, let's get into our first demo. So we've got two topics that we want to cover, both the statistics toolbox and the curve fitting toolbox. So I have two demos, and there's a bit of both, a little bit of both in the second one, but the first one's mainly going to focus on the statistical capabilities in the statistics toolbox. So what we have here is an engine cooling fan. We're going to try and optimize the fan so that it can move more air through the radiator and cool our engine more efficiently. So you can imagine you're in a design process, perhaps in this case you're an automotive engineer, and you have an existing design that works, but someone else has changed another component of your system. So the engine folks have come to you and they say, we've just increased the output of our engine by 20 horsepower, and we're really excited, but now it generates more heat. So we're wondering if you can continue to cool our engine with the existing solution, or if you can find the most cost-effective way to continue to cool our engine. So in this case, we go to our existing design, and then we find if we explore some of the parameters that we have at our disposal to tweak it, and we can see if we can come up with a new optimal solution. So in this particular case, I'm going to have three different parameters I can tune. My current airflow is about 23 or 24 cubic meters per second, and my target is to raise that about 1 meter per minute. The things I can change include the clearance between the fan and the radiator, so I can move it physically closer to the radiator. I can also change characteristics of my blades. I can change their angle of attack against the air, and I can also change how close they come to the shroud housing. So those are the three things I'm going to be tweaking, and we're going to see what effect they have on the overall system. So you can imagine that statistics is going to play a pretty important role in this, because we're going to be looking for some statistical data from our existing assembly process. We're going to be looking at maybe a design of experiments to see if we can determine what some optimal parameters are, and we'll just see where this takes us. So with that, let's go into MATLAB. So this is MATLAB, for those of you who may be seeing it for the first time. There's a couple components. We've got a current directory browser, we've got a command history, we've got a workspace, and we've got a command window. I'll introduce them briefly as we need them, starting with the current directory browser. So this is just a window into the file system, and in this particular case, I'm going to change directory to a location where I actually have my original fan data. So we're going to open this outside of MATLAB to start in Microsoft Excel. And we see we just have a column of numbers, and each of these is a part that came off our assembly line. It's a fan. And we mounted it on a test fixture, and we just measured how much airflow it has. So we've got some statistical data from a number of different experiments. And if we scroll down, we'll find that there's actually 10,000 different measurements that we have here. So the first thing we'd like to do is we'd like to do some data analysis on this. So our first step is to get access to our data. So MATLAB allows you to import data very easily, particularly from Excel files, comma-separated value files, databases, images. Basically, if it's a data source that an engineer or a scientist would need to get data from, we've built tools to help you get that data directly. So in this case, I'm going to import my airflow data, and you can see it's 10,000 elements and one column tall. I have a couple components here I'm going to be checking. So here is my Generate M file checkbox, and when I click Finish, I'm going to get two things. One, I'm going to get this variable airflow. It's going to appear in my workspace browser, and the second thing that's going to happen is I'm going to open up the editor with this untitled file. So let's put this untitled file away for a second, the editor, and let's focus instead on just the airflow. So this is the first thing we got. This is the actual raw numbers from our Excel document. And the workspace browser is a place where you can keep track of the variables that you're working on. So I have here airflow. It's all my data from my Excel file, and it's stored at the maximum machine precision of my computer. It's a double precision number. And in addition to the raw numbers, I have some statistical numbers available here in the workspace also. So you can see I've got its values, double precision, its size. I also have the minimum value in all my data set, the maximum data in all my data set, the mean, the median. I can add some additional statistical information here, such as the range or perhaps the standard deviation. So I can start to get a feel for the characteristics of my system and my data and determine how variable this random process really is. So this is just what's built into the workspace browser. The workspace browser is a place where I keep track of my variables, such as airflow. These can be variables I've either created or imported. On this variable, and it will process all of the data and return the average. Look at the mode or the standard deviation. I can also plot my data. So MATLAB has great visualization capabilities, so I'm just going to start with a plot of airflow. Now, as you recall, our current average was around 23 to 24 cubic meters per minute. And this looks like it's right in line with what we expected. And our goal is 24.8 cubic meters per minute. So our goal is well above all of our data here. So let me just quickly convert this figure into something that's a little bit more useful for me as a person trying to interpret this data. So the first thing I'm going to do is I'm going to add some basic data statistics on this, and I'm going to add it directly to the figure. So the figure windows allow you to add basic statistics directly to your figure. So I'm interested in the mean, the max. So this has now defined the complete range of my data, the min to the max. And I'm also interested in maybe the mean and single standard deviation. So I have 10,000 data points, but with just a few checkboxes, I've now reduced my data into basically 4 meaningful quantities: a maximum, a minimum, so now I've got all my data bounded, an average or mean, so now I have kind of the middle of my data, and some kind of measure on how greatly it's varying, which is this pink line here. I'm going to go one step further, and I'm actually going to draw my target line on this particular figure. Because we're going to be applying some other statistical methods, including design of experiments, to see if we can reach our targeted goal at some point in the future. So right now, I've just opened up Plot Tools. You can access Plot Tools by hitting this button in the figure window. And what it does is it gives you a customizable browser or set of tools that let you tweak the figure as you like. For example, the first thing I'm going to do is the airflow is currently drawn as a line, and these are distinct elements, so I better get rid of my line and just replace them, for example, with little dots. Also, these lines, which represent the kind of the statistical features of my data, are a little bit thin, so I'm just going to increase their thickness so they're easier to see. All right, lighten up my data too. So I mentioned I want that target line, and we have a 24.8 is our recommended target. So let me just pop out my figure window and back over to MATLAB for a second. I'm going to create some new data that's going to start at 1 and end at 10,000. This is my x value. And then my y at both ends of this line I want to be my targeted value or my requirement, which is 24.8. So all I'm doing is really defining a line with my x and y variables. And I'm going to come in here to my plot tools or my figure window, and I'm going to add that data on my plot so I can see it as an upper limit or a target that I'm trying to get to. All right, now it's up here. Of course, it's difficult to see the line because it's right on the edge. So for the last thing I'm going to do, I'm just going to clean up my figure a little bit, including changing my y limits to something a little bit smaller and a little bit bigger. Add some labels. So this is test airflow in meters cubed per minute. And this is the X label is our fan number. All right, so there's our visualization. We have our statistical data on the bottom, and we have our target on the top, which is this green line. Put away plot tools. And also, I'm going to use MATLAB's built-in code generation capabilities to give me a function that will redo this figure again in the future. So we're going to be pulling on the automatic code generation because it's a useful feature throughout the analysis process. And there are also some built-in tools with both the statistics toolbox and the curve fitting toolbox that we're going to build some nice functions that we want to capture. And some of these tools have the built-in ability to generate code as well. So this is now the second time I've generated code, and this is my create figure 1. So let me go ahead and save this. Call it create figure simply. And Let's go back to our untitled and take a look at this one as well. So this is the first function that was created when we imported our data. And it's another automatically generated piece of the puzzle. And what this will do is it will reload my data from an arbitrary file using the same sort of technique that we did interactively the first time. So let me call this import file, save it, replace the existing one. All right. So now we have two functions. We have import data. I'm going to delete my variables. So I have import file, which can import any data file I provide it, but in this case, we just want to import our original data file .xls. It's going to reload our data and populate it in our workspace. And we've got our create figure function. Now, before I call our create figure function, I'm going to edit it a little bit. So all of this code that we're working with is, whether it's MATLAB generated or written by you, the user, it's still going to be adjustable or rewritable or configurable after you get it. So two of the inputs here are this x and y vector that I had passed to create figure to draw my target line, and I'd just like to compute those right in my function. It's not something I want to have the control over outside of my function. So one of the additional tools that we have over here in the MATLAB desktop is the command history, which keeps track of all the commands we've already executed and allows us to pull them in and reuse them again in the future. So in this case, I created x1 and y1. I'm just going to drag those in, and now I no longer need to pass them to create figure. Okay, so now I can call create figure, pass it airflow, and we get our analysis. Oops, one other thing I forgot to do is generally MATLAB honors all of the things that you change when you're working with plot tools. So when you automatically generate that code, it will preserve everything. One of the places where we struggle is what to do with the axis limits that you've requested. So if you request axis limits, it's usually because you want a certain characteristic or feel to your figure windows. But at the same time, you could be restricting your view to something smaller than your actual data set. So you could hand off a function with explicitly defined axis limits, and then if you have an outlier, the person who's using that function will not detect it or will not know. So by default, we do provide those in the code, but they're just commented out, so you can get your axis limits back just by uncommenting them. All right, so let's call create figure again. Oops. And now we have the axis limits we had asked for. We have our target up here, and we have our actual data right here. As we dig through this code, you'll see that the statistical methods that we employed to get us our mean, median, and max are not hard-coded, but rather the actual code for them is directly in our figure. So the computation of the mean is in here, the plotting of the mean line, the standard deviation, and so forth. So what this means to you is that even if we come in here and we characteristically change our data, for example, let me take my original data and create a new data set, airflow 2, and I increase it by, say, 0.25 meters per second, or meters cubed per minute, and I also add in a little randomness. That's just a single random number, but you get the idea. Oops. Just add something. I can reuse the same function, and it will regenerate a new result based on the characteristics of the new data. So just because I have changed my data, my program still works. It'll still compute the range, the median, the mode, or whatever I've put in here. In this case, the mean and the standard deviation. All right. So that's kind of the basic statistical capabilities in MATLAB. I'd like to go a little bit further and explore this data in greater depth, including getting into some design of experiments and maybe a little optimization at the end, although I won't spend much time on that. So before we transition into this script that I have to perform all of this work, I want to talk a little bit about the command window for those of you who are new to MATLAB. I have these commands that I can execute. So my analysis essentially starts up here. I import some data, I do some visualization, I can do some additional statistics, but these should all be cascaded in order, in whatever order I need in order to make sense of my data. Now, no one likes to type all these things out one at a time unless they're in the creative mode. Once you have something that's locked down and working, you want to have a script or a function that can perform these routines for you. So the command history in this case is very useful because you can come into it. Let me double click and make this maximized. You can come into it and have a look at everything you've tried today and pick out the pieces that are important to your analysis. Once you have those, you can create an M file or a MATLAB file that will allow you to perform these in order. So I'm going to create a little script here, script for analysis. This analyzes my data, blah, blah, blah. Import data. Create figure. And maybe in the end, we're going to move into design of experiments. So we haven't gotten here yet. So let me just add a comment here. But the script I have, untitled, is a collection of everything I want to do. Now, it's only got two commands in here right now, import file and create figure. But let me clear my variables for a second and select the top. I'm going to click this button here, which is publish untitled.m. What this will do is it will run all my code. It'll automatically do the importing, the analysis, and it will actually accomplish the final step as well, which is publishing it to some sort of output. So right now I have a very quick HTML document that imports some files and creates a visualization. But I also have available a larger script, engine airflow analysis .m, which I will also publish. And this is going to go through more steps or more work in this process. So you can see this is a much bigger script. It still imports the data. Oops. I modified my create figure. So in the original version of the create figure, I actually had as an optional argument the target that we want, 24.8. But when I rebuilt it, I took that component out. So let me fix that real quick. The nice part about the publish is that even though my publish didn't work, all I have to do is come in and change a small part of my code to debug it, and then re-click the publish button. It will redo the loading, the analysis, and the generation of the report at the end. Oh, and I call that function twice, so let me do this one more time. There it is. Rerun the publishing for the last time, hopefully. So this is the design of experiments cube. We'll talk about this in a minute. This is the redoing of the analysis. These are some response curves, a response function, and then an optimal point. So we'll step through the statistics of this as we go along. But this is the more complete report. The importing of the data, the visualization, the creating the analysis, a little doing some design of experiments work, going out doing some experiments and then bringing back the test results and loading them, analyzing them in this report, and ultimately checking some of the the parameters of our system to determine what some sort of optimal combination of those three variables we can tweak will result in the maximum airflow. And then finally, the display of our optimal airflow at the bottom. Okay, so clearing up a little bit. So these are little shortcut buttons that I'm clicking on. They just have MATLAB commands in them. And when you click on them, they just execute all the MATLAB commands that you see. So that's going to close all my windows, clear all my data, and also clean up my command window with a CLC. So let's step through this one section at a time and take a look at what is occurring as we go through this script and how we're using statistics to help us analyze our data and determine what experiments we need to do. So I'm going to be using these cells that I defined with the 2% signs to step through my code one section at a time. Specifically, I'm going to click this button and it will evaluate a cell, all the code in that cell, and then move to the next cell on the list. So this first cell that you see highlighted in cyan, it has no code in it. It only has comments. So clicking on it doesn't do anything. This will load some data, and it will use the import file that we just created. So I'm going to click on this, and we should see some variables appear in our workspace. And there's our airflow again. Create figure, we've already done this component. So this is going to help us determine what our 10,000 results actually boil down to when we look at them from a pure aggregate statistics point of view. Now, let's get into some design of experiments. So in order to test something efficiently, there are some rules you can apply in order to minimize the number of laboratory experiments that you need. This is the foundation of design of experiments, how you craft your experiment in order to minimize something, either the number of tests you want to do or make sure you have the proper redundancy. There's a number of different techniques to do design of experiments, and one of them is BB design, Box-Behnken design. We've got the documentation here, and you can see it's a part of the statistics toolbox, and it talks about what you can use the BB design for and some of the parameters you can change as to how you want to use it. So if you have 3 factors you want to test, which in our case we do, you could use Box-Behnken design 3. This will tell you what space you want to test. So a -1 is the minimum extreme of a particular number, and a +1 is the positive extreme of a particular number, and then 0 represents the exact middle of the road for a number. So in this case, if you have 3 parameters, you'd want to do the first parameter for the first test at its minimum value, the second parameter at its minimum value, and the third value at its average value. And we've got a space here where all of these are unique tests, and then you have 3 identical tests where they're all done at the average. And you can even see in the documentation, it talks about the center point, and these are the 3 points we'll use to kind of check our our average, make sure our tests are repeatable. So that can be a factor as well. Right. If you're interested in more information on not just Box-Behnken design, but design of experiments as a whole, our documentation is excellent. We have a number of different help files or pages on different capabilities that we have within MATLAB. So not just design of experiments. So these are all the release notes, but also other things such as multivariate distributions that you can see immediately, hypothesis testing, design of experiments, and so forth. In fact, if we dig into the statistics toolbox, we have a wide variety of documentation available in the statistics toolbox, including getting started guides, examples, and a function list. regression testing, multivariate analysis. We don't have time to go into all of these, but here we have design of experiments. It talks a little bit about it and the different options available at your disposal. So there's a little mini primer on design of experiments and what it means to do design of experiments. So let's get back to the BB design and see what that actually outputs. So we've got our test points. We've seen it in the documentation. Let's go ahead and just run this line of code. I now have test points, and these are the extremes of our workspace. So we have our pitch, our distance from our fan to our radiator, we have our pitch angle, and we also have our shroud housing clearances. So that could represent our 3 columns. Now right now we don't have very interesting column headers, but we can add them by using another feature in the statistics toolbox, which is the data set. The data set is a useful way to store data that's statistical in nature, or contains a number of observations that you want to do statistics on. So you can create these data sets and kind of characterize different aspects. For example, you can name your columns or put in some notion of metadata. So let's go ahead and create a data set, and I'm going to use my test points, and I'm going to label the 3 columns: distance, pitch, and clearance. Let me go ahead and create my design. So it's the same information in this figure, but you can now see that my design, instead of just having raw numbers, also has some column headings: distance, pitch, and clearance. And I can access these excuse me, using dot notation. So we've got our pitch column. I can also do some things like give me the distance column. Oops. And I can also perform functions on entire things using the data set array syntax. So there's a whole syntax to how you apply different functions to your entire data set array. So, all right. Now that we have our data set design, and it has column names that we can reference a couple different ways, the next thing we want to do is actually apply our limits. So -1 and 1 doesn't mean as much as the actual limits, 2.5, which is the minimum, and 4 for those particular cases. So we're going to go back into our data set and apply one of those functions, including the limits, which will specify what our distance clearance should be for our design limits. So let's go ahead and evaluate that line. Oops. Evaluate both lines. There we go. And now we have our design limits, which is another data set object, which contains the minimum, the pitch, the clearance, and the distance, the pitch, and the clearance. Now the last thing I want to do is I want to use the interp1 function to replace the -1 and 1 that we have in this data set with the actual values that they represent from this data set. So all the -1s for distance we should replace with 2.5. All of the 1s we should replace with 4. And all of the 0s would be 4 plus 2.5 quantity divided by 2. So 3.25. Evaluate that section. And now our design contains the actual values that we want to test based on the design of experiments work that was set up with the BB design function. This looks like something great we could hand off to a tech or an intern, or we could take ourselves to the lab and perform the experiments. So it's just a list of tests that we need to run. If we look at those on a cube, because we have extremes and middle points, we just have these data points all around and then a point in the middle. So we're really testing the edge of our space, and we hopefully will find an optimal solution somewhere within this cube. So we hand off our results, someone performs some tests, they bring back to us the test results, which I have in a separate Excel file. I don't need to re-import it and regenerate a function. I can reuse import file. Once I have that data, which will come out as runs and output, I can store it into my design, and then I can take a look at the runs, the pitch, the clearance, and so forth. So let me just evaluate this cell. We have our design. So now we have our run number, our distance, our pitch, our clearance, and our final output. So this is the total output in cubic meters per minute from these various test runs. We can reuse our create figure function, and we can see that, let's just move this out of the way for a moment. This blue dashed line is the maximum of our entire data set. So we've got some data points in here. We only have a few of them, so they're a little bit harder to see because I made small dots for our icons. But this is our target line. So we have some values that are beyond our target line. So our test has revealed at least one data point that will satisfy our minimum airflow condition. So let's go in there and find it and actually go a step further and find an optimal solution. So I'm going to go a little faster now. We're going to pull out some information, and we're going to use that information to visualize our responses. So we've got 3 different variables. If we just look at 2 variables at a time, what effect do they have on our system? So let's first look at clearance and distance. So we've got clearance and distance, and the red is more airflow, and the blue is less airflow. Snap to a downward looking view. You can see that we get the maximum when our clearance is minimized and our distance is minimized. So these are relatively easy things to do, and they're pretty much what we'd expect. The smaller the clearance, the more airflow we'd get through. The closer we are to the fan, the more airflow we get through, because the less space it has to leak away out the sides. So this is pretty much reasonable, but there's not a lot of change from left to right. I mean, we're really only talking about 25 to about 24.7, a very small change. We get a lot more action, actually, on the pitch. So the pitch is interesting. So I'm just comparing against distance in this case, because we definitely have a maximum that's in the middle. So there's a pitch angle that's way too shallow, and as we get steeper and steeper, we reach something that's kind of the sweet spot. And then as we go further, we experience not only diminishing returns, but we get diminishing airflow, so we get negative returns as we increase our pitch angle. So there's something interesting to be found here. Of course, as you get even more than 3 variables, it becomes more difficult to visualize these responses. So we have another function in our statistics toolbox. Of course, as you get even more than 3 variables, it becomes more difficult to visualize these responses. So we have another function in our statistics toolbox, the response tool, which is an interactive tool which allows you to explore your data more fully. Let me just run this thing. We could take a peek at it. What I have here is the 3 different variables now, the clearance, the pitch, and the distance, and I can see what effect they have on the airflow, and I can expect, based on my experiments, the total amount of variability that I actually have based on my data. So my airflow for this combination is expected to be 24.8 plus or minus about 0.17. And I can try different combinations. For example, I can set this to 2, and I can set this to 0.6, and it will just try different things. I can also grab these lines and I can graphically move these. So I know that when my distance and my clearance are minimized, I have the best airflow. But now I can come in here and I can kind of dial into my pitch value, which maximizes these. And you can see that with this particular combination, minimum clearance, minimum distance, but a pitch of about 0.56 radians, I get my max airflow of about 25.0 cubic meters per minute. But you can see my variability is also pretty high at this point. So this is an example of one tool you can use in the statistics toolbox. You can also use the optimization toolbox. We have a whole webinar on that, so I won't go into that in detail. But the optimization tool is very similar to the statistics toolbox. It's got some built-in functions that allow you to set up an optimization, minimums, maximums, and determine kind of your optimal solution. So in this case, I'm just going to load the results of my optimization rather than run them. And we can see on this cube, it's what we found graphically with the response tools, the same response that the optimization toolbox found. It's minimum clearance, minimum distance, and then a blade pitch angle of about 0.56 or thereabouts. So we can go back to our team and say, build your faster motor. We'll be able to cool it. We had something we wanted, we had some factors we could change to reach our target. We applied some statistics to look at the data that we had, and we used the response tool as well as design of experiments to kind of characterize how changing different variables would actually result in the performance that we wanted. So in this particular example, we're using MATLAB to do our data analysis. So MATLAB was the factor that kind of tied these steps together. We were able to import our data very easily from files. We were able to do our data analysis and modeling directly in MATLAB, and we were ultimately able to both generate a report and generate these optimal design parameters.